This example is for a mass on a spring with friction. And so over here I've got my little diagram. So this is meant to be a solid object. It's actually on some horizontal surface. And we've got a mass, M, some block. I've got a spring that's attached to the wall. It has a spring constant K. And then there's also friction when it's just sliding over this horizontal surface. And there's a friction constant B. And we also have its initial condition. So going back here, we're going to have in this particular example, the mass M is 1 kilogram. The friction coefficient B is going to be 0.1 kilograms per second. The spring constant K is equal to 10 kilograms per second squared. And at time 0 seconds, the position Z is negative 0.3 meters, which is right here. And the velocity at time 0 seconds, Z prime, is positive 1 meters per second. And so the Z equals 0 here is the rest position of the spring. So if we put the block at Z equals 0, it wouldn't have any force from the spring. It wouldn't go forward, it wouldn't go backwards, it would just sit there. And the reason for that is we want, when the spring is extended past the rest position, it is pulling backwards. When the spring is compressed prior to the rest position for negative Z, it's pushing forwards. That's the idea. So here we have two initial conditions, and this is the differential equation that we have. So we have force equals mass times acceleration. So Z is position. So the second derivative will be acceleration, and mass times acceleration here. That has to balance with all the other forces acting on it. So the sum of all the forces equal to 0. The friction is B times Z prime, and the spring force is K times the position Z. All right, so the first thing to emphasize here is we need both initial conditions to determine what it will be in the future, right? We need to know where it is initially. If I give you the spring with this mass on it, I need to tell you where it is when I start my experiment at time t equals 0 seconds. I also need to tell you how fast it's going, in particular, which velocity. Is it, did I let it go and it has 0 meters per second? Is it moving to the left with a negative velocity? Is it moving to the right with a positive velocity? How much? You need to know both pieces of information. You need to know where it is when it starts, and you need to know what its velocity when the experiment starts. So this is kind of intuitively why we need both of these initial conditions to determine what the spring will do in the future after 0 seconds. And then for the differential equation, so if we actually write this out, so M is 1, B is, 0.1, K is 10. So we end up with this differential equation. 1 times Z double prime, so Z double prime plus 0.1 Z prime plus 10 Z equals 0. And we have these initial conditions. Z at time 0 is equal to negative 0.3, and Z prime at time 0 is equal to positive 1. So you don't know how to solve this yet, but the general solution to this ordinary differential equation is Z of t is some constant C1 times e to the negative 0.5t times sine of this number, which is if you work out the problem, it ends up being calculated from all the constants that are specified, but just take it for granted now. So sine of 3.16188 times t, then plus another constant, C2, which is different from C1, times e to the negative 0.5t cosine of 3.16188t. So now we have the solution that can accommodate absolutely any initial conditions. So it could start at any initial position, it could start with any initial velocity. And the C1 and C2 allow us to solve for both the initial position and the initial velocity, right? We have essentially two constraints that we have to satisfy, two equations, and we have two unknowns that we can use to satisfy those equations here. And so it turns out to satisfy Z of 0 is equal to negative 0.3, and Z prime of 0 is equal to 1. The constants end up being C1 is equal to 0.31523, and C2 is equal to negative 0.3. And so the whole solution ends up being this mess. But intuitively, that's why we have as many initial conditions as there are degree for the system. So this is a second order ordinary differential equation. We need to know Z at time 0, Z prime at time 0, and physically we need that. In the spring example, we need to know where it is and what its velocity is when we start the experiment. So intuitively, that's why we need both initial conditions. And if we had a third order differential equation, which doesn't happen a whole lot in physics, we would need 3 initial conditions and we'd end up with 3 constants to solve for in the general solution.